your TA in this quarter. And today's topic is Kirchhoff voltage and current law, as well as basic circuits. There will be 8 discussions in this quarter, and we'll have 1 topic per discussion. I totally understand the difficulty for people who learn this for the first time because I was because I had this course when I was undergrad. So the structure for today's discussion will be confusing concepts and some exercises. My office hour is right after the discussion, so feel free to ask me questions. So let's start with the confusing concepts first. For students who are not with ECE background, a lot of terminologies may seem strange in the first chapter. When I learned it for the first time, the reference and how to define the reference direction or polarity is a big challenge for me. We need to notice that the reference term for voltage and current are different. For voltage, we call it reference polarity. And the polarity consists of positive and negative reference. To quickly show you guys, we can imagine it as a set of stairs. And the higher end is the positive one, and the lower end is the negative reference. And for the current, we call it reference direction. Different from the definition of voltage reference, the direction does not have positive and negative ends. It's just like a car running on a road. It's just an arrow pointing at the direction. Okay, so up to now we are good. But once the reference encounters a word called passive configuration, it is easy to get messy. So it's time to introduce passive configuration. Passive configuration, it sounds like a big word, but basically it is just some rules for people to follow, so it becomes more convenient for them to communicate on the properties of a circuit. So frankly speaking, it is just how you combine the reference polarity of a voltage and the reference direction of the current. So it's how you combined the reference polarity and the reference direction. For you to memorize it easily, let's imagine here are the stairs, just like we talked about before, and this is a positive and negative reference of the voltage, and then a car is running down the stairs naturally. So this is an analogy of the passive configuration, where the reference direction of the current flows into the positive reference of the voltage and flows out at the negative reference. So when you see a car running down the stairs, that means it is following the passive configuration. When you see a car is running up the stairs, it is not following the passive configuration. And some people will ask, why does it matter? Okay, so if you're following the passive configuration, the power P is equal to voltage times current. But for the reference not following the passive configuration, like this, the car is running up the stairs, the power is equal to minus V times I. So we need to be careful of the minus here, which means not following the passive configuration. At this step, you still cannot tell if the element is absorbing or supplying energy because you don't know the polarity of the values of V and I. So let's come to next step, how to determine its positive or negative value. As we know, before we solve the circuits, we don't know the real direction of current. We don't know the real polarity of voltages. We define the reference direction and polarity just for convenience. So we have something to refer to. So all of that are just a guess. Suppose you're given an element which is A, and you don't know which side is a positive side. So you just assume the reference positive end is on the left and the negative end is on the right. And after some calculation, you get the result that the voltage here is 5 volts, which means that it is following your definition of the reference polarity. It is actually a stairs following your guess. But sometimes, which is also normal, after some calculation, we find out that V2 equals to minus 5 volt. Which means that actually the stairs is going up instead of going down. So it is equal to 5 volts if you exchange the negative and positive ends. So back to the previous point, when we would like to determine if an element is absorbing or supplying energy, we need to consider both the side in the equation here, as well as the size of the value, which refers to number 2. Combining size at 1 and 2, we can get the final values of P, and then we can determine if it is absorbing or supplying energy. Okay? Great. So the first 3 points are about references, and number 4 is about how to memorize Kirchhoff's voltage law and Kirchhoff's current law. We need to understand them and then memorize them. First, let's consider KVL. KVL defines that within a loop, the algebraic 怎么说呢？ algebraic. The KVL means the KVL defines that the KVL concludes that within a loop of a circuit, the algebraic sum of voltages equals to 0. Okay, the idea behind this law is the conservation of energy. So energy, for example, in this circuit within the loop, the energy is supplied by the voltage source on the left and absorbed by the resistance on the right. If the sum of the voltages is not equal to 0, as time goes by, the energy difference will accumulate, which results in the mismatch between the energy supplied and energy absorbed. And this is not obeying the conservation of energy. So we can go back to the conclusion that the energy supplied is always equal to energies absorbed. So minus Vs plus Vr is 0. Now let's consider KCl. The idea behind KCl is electrons are always running. If the electrons don't run, the current is equal to 0 because the flow rate is 0. So when current is 0, we don't need to consider them. And if they are running, or the electrons come into a node, we also goes out of the node. It's like a transfer station. So we say or the current flowing in are equals to currents going out. Do you feel it is easier to memorize these two laws? And let's come to the fifth point, which is also the last point, the confusing concepts. It is the annotation. In the textbooks or homework or the lecture materials, you'll encounter many kinds of annotation. Some of them are named by numbers. For example, V1, V2, I1, I2, blah blah blah. And sometimes they are named by alphabets, like VA, VB, or XY, etc. And sometimes they are named by the electronic elements. For example, VS, IS often means the properties of the sources, and R usually means resistance. And the first three are the naming rules with only one subscript. Sometimes we have double subscript. And you should be careful to use double subscripts with the reference rules we mentioned before. Let me give you a simple example. So here is a resistance between node A and node B. So we can name the current IAB, okay? If we say IBA, it means the direction is from B to A. And equivalently, we can also name it I1 or IR. Which annotation you choose, it doesn't matter as long as they make sense, alright? So these 5 points belong to confusing concepts, the first part. Now let's come to the exercise part. Exercise. Some of the exercise may overlap with Weinan, another TA in this class. Problem 1 is about KCL. Let me draw it bigger. So here is a figure from the textbook, but I changed the values. Let's give some reference direction. This is I of A. This is I of B, which has a null value, 1 ampere. And the current here is IX, which equals to 4 amps. And here is IE, which equals to 2 amp, is also known. Now please calculate, or the unknown current. It may seem a bit complex at first sight, but as long as we apply KCL at each node, it will get solved properly. Let's consider node 1 first. For node 1, we have current flowing out equals to current flowing in, which is 0 here. So we get I of A is minus 1 amp, right? This is the most direct current for us to solve. And then let's take a look at node 2. Currents going in, IB plus IC equals to current going out. So we can compute that. IC equals to IX minus IB, 4 amps minus 1 amp, resulting in 3 amps. So IC is also solved here. And then let's take a look at node 3. Again, currents going in, IX plus IE equals to current going out. So ID equals to 4 amps plus 2 amps equals to 6 amps. A, B, C, D, E. So all the currents are solved already, just using our current law. Haha. So for more complex circuits, you may need to consider more nodes, and what you need is just patience. Compute them one by one and you'll be happy. Now let's come to problem 2, which will check your understanding of KVL. Alright, so let me draw the figure for Okay, so we have A, B, C, D, E, F, 6 elements in this circuit. And let's define the reference polarity of all the currents. You can give different reference polarities as I did, as long as your values does not contradict. So the values and the reference direction or polarity change correspondingly. Okay, so assume we know that V of A equals to 10 volts, and V of B equals to 5 volts, and V of E equals to 3 volts. Can you solve for the rest? So because this is an exercise of KVL, we just need to apply KVL at different loops. So let's consider VC first. So here is a loop going through element A, B, and C. For loop A, following the voltage law, we can see equals to 0. So VC equals to VA minus VB equals to 10 volts minus 5 volts, which is also 5 volts. So we know that VC equals to 5 volts, right? And for the second loop, going through B, D, and E, you can see that VD minus VE minus VB equals to 0. And VE equals to VD minus VB, 3 volts minus 5 volts. We can see VE equals to minus 2 volts, right? As we already know VC and VE, the rest voltage will be feasible to solve. Let's take a look at loop 3 going through CEF. Plus VE minus VF because the current is flowing in the negative reference, and then minus VC equals to 0. So we know that VF equals to VE minus VC. VF equals to minus 2 volts, minus 5 volts. VF equals to minus 7 volts. And how can we verify if we calculate correctly? This is not necessary when you solve a problem, but you can check it yourself. It is verifying. Let's choose a loop that we never used before. For example, the outer loop. Okay, the outer loop goes through A, D, and F. Let's check. VA equals to 10. Sorry, minus 10, 3 volts, and minus 7 volts. What is it? It is 0. So our computation is correct. Great. Now let's take a look at problem 3. By the way, congratulations that you have solved the 2 important problems in this chapters. And then the problem 3 is about the equivalent resistance. We learned 2 relationships of the resistances. The first one is in series, the second is in parallel. In the following chapters, you'll encounter more complicated relationship that you can't simply describe by series and parallel. In that case, you use other techniques to compute the total resistance. But in this chapter, up to now, we can just use the rules of series and parallel resistance to solve the problems. So for resistances in series, the total equivalent resistance is equal to the sum of all the resistance in series. And for resistance in parallel, the equivalent value is equals to 1 over the sum of 1 over R of I. Let me draw a figure for you. At the beginning, it may seem confusing. It seems like they are not strictly in series or parallel. This is because the resistance in these circuits are not put in an intuitive way. So let's reorganize this circuit to make it better looking. And how do we do it? Remember, every point in the ideal conductor can be seen as one node. So for node X and node Y, they're actually the same. Node X equals to node Y. And so the element between X and Z is equivalent to say that it is between Y and Z. In this way, we observe that the 3 omega resistance here is between X and Z, and the resistance of 6 omega here is between Y and Z. They are between the same sets of nodes, which is to say they are in parallel. So let's move the Y nodes here all the way to overlap with X. What will happen? Copy this. Does it look clear now? So the equivalent of the 3 omega and 6 omega in parallel here is 1 over 1 over 3 plus 1 over 6 is equals to 2 omega. You don't need to give this, you don't need to draw every step in your answer, but for you to, so this is just, you don't need to draw the step-by-step circuit figure. I draw it just for your convenience in a tutorial, so you don't need to do this in the exam. So here, let's replace this 2 resistance with its equivalent 2 omega here. All right, and let's continue to compute the equivalent value of these two resistances in the series. Okay, so things become clearer and clearer now. One over 12 of omega, 6 omega, 4 omega. So we get the result that the R total is equal to 4 omega. So the key idea behind this kind of exercise is remember that every point on an ideal conductor is equivalent, and you can make it shorter, longer. You can move the node all the way along the conductor. That is the key to the solution. If you want more exercise about calculating the equivalent resistances, you guys can refer to Weinan's discussion and also to the homework. Thank you. Hope this helps. This is the end of the discussion 1. Goodbye. See you next time.